Okay, well, we're back to this talk we have here after lunch here, more basic science and these laws of science. So I wanted to have a definition of a science law as we've worked on those and discovered those over the years. A pattern in nature that it's followed without exception, a basic law. And you know some of these, the law of gravity and energy and those kind of places that we will kind of explore together. Now, the man-made laws we come up with, speed limits or whatever, you can break those laws, but try breaking these. You'll be in trouble. You know, they hold fast. There are some other words involved with this kind of thing, and I was just putting some here. There's something called a hypothesis, which is sort of an educated guess, kind of like early stages of studying nature. And then there's something called a theory, which could be widely accepted. It may or may not be true. There's the theory of plate tectonics, seafloor spreading, drift of the continents. I think there's some truth there. But then there's also evolutionary theory, which is not so much. So it kind of goes up a hierarchy, probably with these laws at the very, very top. You know, science has been so successful with this stuff, with the scientific method, doing experiments, and then coming up with new products and new ideas and solutions to problems. I mean, just look around at all the technology and the electricity and everything that we have. Because it's been so successful, many other disciplines have tried to get under the umbrella of science, as if that word is sort of magical. And since I'm thinking of basic science ideas here, let me put another word on the screen, the social sciences. Well, this includes things like economics, history, business, psychology, a whole bunch of these areas that also use the word science because they like it, because they can see how successful the natural sciences have been. And I was thinking about that, the social sciences, and I left a question mark on it. In physics and chemistry and geology, we come up with formulas, and we looked at some of those in our math time earlier this morning. But in the social sciences, have they come up with laws? Have they come up with unbreakable rules in those areas, in psychology or in economics? I don't think so. Now, I guess you can call it science, which is the search for truth, but it's really a separate category. And I almost feel for the folks in social science. Their main challenge in that whole area, you're working with people. And when you have people involved, there are so many variables you can't nail it down. Now, they'll say that, like in economics, that they have laws, like the law of supply and demand, but there's not really a formula for it, and it doesn't hold fast like F equals ma or some of our other physics formulas. So anyway, I've just seen that word social science. It's fine to use that word, trying to figure things out in the search for truth, but it's a whole different realm from the natural sciences. And let me show you what I want to do here for my part of this talk here, for an outline. And first of all, we're going to talk a little bit about the laws of nature. I want to show how they illustrate design, patterns, complexity. Also want to show how these laws are constant. They hold fast. They make the whole place dependable. Things aren't slipping around and changing. And then there's just two examples of laws. I want to talk about gravity, which is very basic, and then something about energy, just to kind of drill down and kind of get narrow in a couple of areas. You could do a lot more, but our time is limited. So that's a brief outline of what we're doing here for the next little bit. So we start by showing the design that's all around us. And in fact, I referred to that this morning, so I just have a picture here. Remember these spirals? Referred to those early? So now here's a whole bunch of them on the screen. It's just a pattern, a design that God must like because it's all around us. In fact, I have 10 different pictures here. Can you recognize some of them, what those are? And it goes like from the small to the large. I believe in that picture there's a centipede in the upper left corner. And that, by the way, down in the lower right corner, that's actually the cochlea inside our ear, which is another kind of spiral. And there's some big ones there. In the middle, there's a hurricane. And at the bottom page there's a galaxy. Boy, these spirals of all shapes and sizes all around us all the time, from small to large. I just see that as a pattern, a repeated pattern that is used throughout creation, throughout nature. Let me show you some more design. Now, this is starting to sound like physical science. Put two things on this screen. In the upper left-hand corner, of course, there's an atom. Remember how that picture goes? Looks like a bullseye target. Actually, that's an argon atom. I can see there are about 18 electrons there. What a neat little system that is. An atom. The size is about 1 angstrom, as it's called, 10 to the minus 10th meters. That is so small. If you're writing like on a sheet of paper, even the thickness of a sheet of paper is like 1,000,000 of those thick. These atoms are incredible, and they can see them these days with these, high-precision microscopes. Anyway, there's an atom, and as you know, those electrons go round and round in perpetual motion, traveling very, very rapidly, like, my goodness, more than 1,000 miles per second, those electrons. That's faster than a bullet. And round they go. But as we study this more closely, we realize that those electrons aren't really in one place. They kind of get spread out all the way around the atom. Electrons are kind of interesting, but anyway, there they are. So there's an atom, and I like that circular pattern that's in nature. All the atoms are like that. Then on a much greater scale, 24 zeros more, there's that other picture of our neighborhood, the solar system. Just to think about that similarity, like that bullseye pattern that God uses on the small scale and the large scale. So anyway, there's the sun in the middle and the planets going around. Remember, we're the third planet. How many trips around the sun have you made? That's as time goes by. And I was just looking at the numbers here. Right now, this afternoon, while we're sitting here, the Earth is moving at about 60,000 miles per hour. You say, it is not. I'm sitting still in this seat. I'm not going anywhere. Well, we better be moving or time will stop. We are going around the sun, and you have to go about that fast. And so 60,000 miles per hour. If you put in a whole day here, from morning till we finish this afternoon, that's about 8 hours. 8 times 60,000. How far will we travel today? Do the math. It's almost 500,000 miles. We should pay you guys mileage. You're really putting them on here. This goes on and on. Fascinating how this all works. Then I look at this picture and I think that atom up there, why doesn't it collapse? You got those electrons. Those are the little red things. Those are negative, remember, minus. And then you got that nucleus in the middle, which is positive. Pluses like minuses. Why don't all the electrons fall in? It's a good thing they don't, but we don't know why. And on the bigger scale there, the solar system, there's that gravity attraction. Why doesn't the Earth fall into the sun? Or why doesn't the Earth take off like a tangent and it gets cold and dark in a hurry? It doesn't happen, and we're not sure the why of it all, but it all operates, of course, according to God's plan. It's a great system. Anyway, just looking a little bit at design and how it all works. So here's another example of patterns. I got to have a couple formulas here on a Saturday afternoon. Some of you are more familiar with these than others, but these are just equations, very basic ones. The one on the left is the gravity equation. The force of attraction is equal to big G, that's the universal constant of gravitation, and then you got the M&Ms, that's two masses, and you divide by the distance between them squared. Now, if you wanted to use this formula, big G, you can look it up, and little m could be your mass, maybe in kilograms. And then the other m could be the mass of the Earth. That'd be the M&Ms. And then if you divide by r, the distance from you to the middle of the Earth, if you put in those numbers, you know what you would get for big F? You'd get your weight. Your weight is an illustration of gravity as the Earth pulls on us. So anyway, that's the gravity formula. Then over on the right-hand side, very similar, very symmetric, is a totally different area. That's the electric force. K is the electric constant. And then you have QQ. Those are two charges, electrical charges, and you divide by the distance squared again. Look how similar they are. I mean, it could have been worse in this whole study of nature and laws, but there's some neat similar arrangements here. That equation on the right, by the way, could be something like lightning. Static electricity in a cloud can separate the charges. So one Q is positive charges, the other Q is negative charges. And they're apart, but they feel this attraction toward each other, plus and minus. And if the force builds up enough, then they go smacking together, and that heats things up when you have a lightning stroke and all that kind of excitement. Well, we could go on and on with these designs and these patterns, but the next thing in our little outline was to talk about constants, that it's also dependable, that things don't change. So let me move into that. And boy, this writing might be too small to see. What I have on the screen here are like 10 letters or abbreviations. So again, I don't know what all our background is, but look those over. Can you identify some of those? These are some of the constants of nature that we measure day by day in the laboratory. Look them over. See how many you can get. I see some of them have Greek letters with them. We run out of our English alphabet. All these symbols, and these are the kind of things you could look up in a handbook, and we continue to learn these more and more accurately. Anyway, did you get some of them? I see we got Avogadro's number in there, NA. There's big G at the bottom, and we got to go on. So I'm just going to put the answers in here. This list could go much further, but here's just some of them, these interesting constants. You don't want to think about this. The word evolution means change, doesn't it? Unrolling, unraveling, changing. And so if there's any truth to that whole worldview, shouldn't these things change? I mean, wouldn't that be consistent, that everything? But they don't. We measure these things, and every year they're exactly the same. There are some constants. Now, it does make life dependable and stable, so it's a good thing they don't change, but that seems to defy the whole approach to evolution where everything changes. These do not change. Let me back a little closer and look at the first one on the list. It's the letter alpha, the Greek letter alpha, and it's called the fine structure constant. I mean, you'd have to be in physics to love that thing, but there it is. And it's kind of an interesting constant. You can actually calculate it with this formula right here, and it has a value like 1 over 137. Kind of a funny way to write it, but that's the way we do. Now, the curious thing about this particular constant, alpha, it has no units. It's a pure number. It's not measured in meters per second or calories or anything else. It's just a number. Usually these constants depend on what system you're in, the metric system, the English system. So there's something very fundamental about this constant. It's the way God set it up, and whatever system of units you have, it comes out to be a value like that. So it's a very special number. Somehow that's one of the building blocks that was used to set up the whole system, the whole cosmos. That was first figured out, by the way, exactly 100 years ago, 1916, by Arnold Sommerfeld, some physicist from yesteryear. And what that constant does, it determines the size of atoms, and it determines the colors of light, and the strength of magnetism, and many other things as well. I like these fundamental constants. They're so fascinating. Now, I'm into this idea of constants in nature. Let me show you another one. This gets a little bit technical, but we can handle it right after lunch. You know, we are all made of 3 small particles. You remember what they are? Protons, electrons, and neutrons. I mean, that's what makes us up. That's what atoms are made out of. How could God take just 3 particles, protons, electrons, and neutrons, and make everything? All the different atoms, all the different elements, different people. What variety you can get with just 3 little particles. But there they are. And we measure these days quite closely their mass. They're very small amounts, but you can measure these. So there it is in kilograms. Look at that. We got those out to 4 decimal points or so. And you can see I kind of put them in the order there, one heavier than the other. Of course, they're all very lightweight. It would take a whole bunch of them to make any movement on a scale. But I'm looking at those numbers there, and there's something interesting about them. Now, I don't even know if you need to absorb all this. And if you want to set this over, you can have a set of this PowerPoint. I'd be glad to give it to you so you can look at it more closely. So I'm just walking through it quickly right now. A neutron. Now, these are small particles that are usually hidden inside the middle of the atom in the nucleus. If a neutron escapes, if you have a free neutron moving around through the air, it won't last very long. It has a half-life of about 10 minutes, and it'll decay. Neutrons are unstable. In fact, as this picture shows, a neutron converts itself into a proton, an electron, and something weird called an antineutrino. There's not going to be any free neutrons around here. They just wouldn't last very long. They just go away. They're radioactive. How nice. Don't need them anyway. They're tucked inside the atom where they're secure. A proton won't do that. So I have that arrow, but I put a line through it. A proton is not heavy enough. It does not have enough mass to decay. If it could, it would turn into that stuff on the bottom of the slide, but it does not happen. So what does all this mean? Who cares? These particles are too small to see anyway. What's the big deal? Well, watch what happens here. If a proton was 0.2 of 1% heavier, then it would decay. They just don't have quite enough mass to fall apart. But if they had a tad more, they would, 0.2 of 1%. Then you say, well, so what again? Who cares whether a proton decays? Well, if a proton was a little bit heavier, then they would go away. And over on the right-hand side, I'm saying, you know, a proton is the same as a hydrogen atom. That's all hydrogen is, with or without its electron. So if protons are a little bit heavier, all the hydrogen would go away. And you say, well, that's getting a little more serious because water, H2O, is made out of hydrogen. So if protons were a little bit heavier, all the water would go away. There goes all that water in those bottles we have around here. And furthermore, the stars are mostly hydrogen. Hydrogen is God's favorite element. The stars are like 90% hydrogen, so all they would go away. This gets interesting. The mass, the heaviness of a proton is carefully chosen so that it's stable, so it doesn't fall apart. And there's the alternative with everything collapsing in a hurry. This shows the extreme balance, just how everything is put together for our well-being. There's a name for this kind of thing. Let me just get rid of all those crazy equations. This is this Goldilocks? The idea, you know, that the porridge is just right. And this is what we find for planet Earth and space and the whole cosmos. Things are just right for our survival. They're neither too hot nor too cold, too heavy or too light. There's this extreme balance that makes life possible. In fact, this is called the anthropic principle, and there it is defined there if you want to read the fine print. This is kind of just current thinking in physics that it appears to us that this place has been set up for our well-being, and we know that it is. This is very bothersome to our secular friends. Why is it that everything is just right so that we can live here? I mean, it almost looks like there's a creator behind it. So you know what the alternative is? A lot of people are now saying it must be that there are other universes where things aren't so good. There are other places where the proton was too heavy and it's all fallen apart by now. They talk about multi-universes to try to get a statistical group so that we're not so special. But it's crazy. This universe is the only one we know about. It's a universe, and it is balanced, and it is designed, and we can see it very well. So anyway, I've been talking about the patterns and the design and the constant. Let me jump out of my physics world for just a minute because we're talking about the laws of nature, and I just want to cover some different areas. So let me just go here a minute. Biology is not my area, but I mean, it's part of our lives. So here's a different kind of law, the law of biogenesis. Now, this is the law that says life always comes from life. You don't have this spontaneous formation of living things. Mice make mice, cats stay cats, biogenesis. And that's a good rule as well. Now, this wasn't always accepted. Back a few centuries ago, like in the Middle Ages, it wasn't realized how complex life was. And there was a thought that if you had a mud puddle outside, the mud could just come together and life might crawl out of it. They didn't realize the complexity of it all. In fact, I found a formula for how you can make mice. Can I share my recipe with you? It went like this. Take some grain and moist rags, put them in the corner of your room for about a week, and mice will show up. You like that one, huh? I got to tell kids, don't try this at home. It might work. you know, mice are always kind of scouting around looking for a nesting place, and if they can get in, they may take over. No, this formula, this was disproved by Louis Pasteur, who took these materials, the grain and the moist rags, and he put them in a sealed container. And if no mice can get in, then the whole thing spoils, breaks down. It's just no good at all. And in fact, he came up with that idea of life from life, the biogenesis law. And so it has ever been. But that is a cute formula before they realized the complexity of life. Now, that doesn't stop these people, and they're still trying to come up with a spontaneous origin of life. So here's an experiment that you'll find in all your biology books. Famous experiment, Stanley Miller, University of Chicago, 1953, where you have this glassware. Looks like a chemistry lab, right? So down in the lower left-hand corner, you have some boiling water, which is supposed to represent the early ocean, when things were warm and long ago. Then you introduce some gases. I see there in the middle of this picture, methane and ammonia. Those are thought to be the gases of the primitive atmosphere on the early Earth. The upper part of that has that vessel, and you make some sparks. That's supposed to be the energy supply, like lightning. So they get this thing going, the water's cooking, and the steam is going round and round. And what is this experiment? Why are they doing this? The hope was that these gas molecules would come together and form life, and something would crawl out of this experiment. Does it work? I don't think so. If it did, there'd be big headlines. The glassware gets all crudted up, and you got to clean it and start over. They've repeated this experiment thousands of times. They're still doing it today, and it just shows the impossibility of the spontaneous origin of life. Now, we've got to be honest here. They do make some things called amino acids in this experiment. They're not really the right ratios. They're not the right kind. And an amino acid, that's a long, long ways from a DNA molecule. Amino acid, maybe 6 atoms. A DNA molecule with 100,000 atoms all carefully in place. This experiment doesn't work, but, bless them. Let them keep doing this kind of research and see what they can find as it goes on and on. Quite a deal that they're into. And since these experiments don't work very well, these days we have this whole urge to go into space and look at other planets to see if there might be life out there. And as we've found out this morning, as far as we can tell, we are unique in this whole universe. So we're talking about the laws of nature here this afternoon, and we'll get to gravity and energy in just a minute here. This morning, we had that talk way back at 9 o'clock, and I was talking about some design in nature, and I just can't resist. I got to give you a couple more examples of this, just for variety this afternoon. And again, as I look at this world, I see all these secrets that God put in nature, just waiting for someone to find, to put to use, so that for our well-being. So I was going to show you a couple more examples of design that I think are quite remarkable. Let's see. Let me go ahead to this picture right here. I'm from Indiana, and we have all these cornfields. And we have found something interesting about corn. In the spring, and you have cornfields out here as well, when corn starts to grow, here we have a corn shoot on the left-hand side. On a sunny day, the sunlight goes right down through the stem of the corn and goes underground and lights up the roots. And if you could somehow dig the soil out of the way, there's light under the soil. This helps the corn to grow, solar energy, along with the water and the nutrients that are in the ground. So there's a name for this, fiber optics. I mean, that's kind of a new idea. They send email around with fiber optics and things like that, but it's in corn already. And it's a whole interesting area, fiber optics. I see that they're putting cables all around the country. Actually, I brought some along here. This looks like fishing line, but this is fiber optics right here. I was going to have a friend. Can you come up and help me for a minute? I got my assistant here who's going to help me because I wanted to show you guys something. Yeah. So maybe you could just stand up here where we could see it. And if you could just kind of hold this, let me give you this other end here. Your name was Markar. Where's the other? Here, can you find the end? Boy, I do need help with this thing. Yeah, and if you could just kind of hold it up like this. Okay, so this is fiber optics, and what I'm going to do is shine a flashlight in this end and see if we can get the light to go out that end. Fiber optics. So it's got a knot in it. That'll be great fun here. We'll see if this works. By the way, if this was a garden hose laying in your backyard in your garden, could you shine a flashlight in one end and get light to come out the other end? A hose? Never tried it, but I don't think so. But this is fiber optics. So I got one of these green lasers here. So we're going to watch the end that Mark was holding. Let me just kind of get it in here. Is it kind of working? As much light as I can get? Is this worth coming out on a Saturday afternoon? Now, really? You're an easy crowd. Yeah. You know, if this was stretched clear across Seattle, the light could come out that other end. If this is good stuff, 100%. Now, with email, they usually use invisible light, probably infrared, but visible works as well. In fact, if this stuff was clear across Washington, I think you could get light to come out the other end. Fiber optics. So they're spending a lot investing on this and trying to improve fiber optics. And what's one thing they're studying? Corn. God's fiber optics. It's been around since day number 3 when God made the plant world. It's one of these countless ideas that God's put there for us to make use of. Thank you. Thank you, Marco, for your use. I had to talk him into coming up here. Appreciate that. I just so enjoy these examples from nature, and it's all God's fingerprint. It's intelligent design. In fact, let me show you one more before I get back into the laws, the technical stuff. So here's a bird called a kingfisher. Our picture's kind of being distorted a little bit, but it is a crazy-looking bird. He's got a little body and a big head, long beak. Looks like he was designed by a committee or something, you know, like they couldn't decide on things. Well, this bird is a master of fishing. It stands up on a branch. You have them here in Washington. And when a minnow goes by, straight down into the water it goes and grabs its lunch. And when it hits the water, there's hardly any splash. These guys ought to be in the Olympics, the high dive, you know, slipping into the water easily. So that's how they operate, a kingfisher. We got them back in the Midwest as well. Well, now, this bird caught the interest of a designer of high-speed trains. Now, over in Japan, they have these bullet trains. They go 200 miles an hour. We don't have anything quite like that in the U.S. They're ahead of us. Japan has these high-speed trains, and they're very safe and successful. And there are mountains in Japan, and these trains are going so fast that they have tunnels. They just shoot on through. Something happens when these high-speed trains go through a tunnel. A cushion of air builds up in front of the train, and when it exits the tunnel, this air expands, and it causes a sonic boom. It makes thunder. It rattles the windows. It wakes people up for miles around. Something has to be done here. And they didn't know quite how to treat this, but again, this train designer, he was also into birds. He got to thinking, you know, this creature here goes from air into water with hardly a splash. It just slips in. It's a huge pressure difference, somewhat similar to a train leaving a tunnel. So he's gotten busy and has redesigned these bullet trains so that the front end, the engine, mimics the shape of the kingfisher bird. And these things work now. They don't make any noise when they leave the tunnel. Altogether, they save 10 or 20% of the energy. I got a kick out of this picture because even the lights on the train, they kind of mimic the nostrils of the bird itself. It's just one more example of design in nature, and they just seem to be endless with us. So anyway, I wanted to fit in a couple more design examples. That could be a whole separate talk, another time, another place. But we're back to the hard stuff here now, so I'm back to these laws of nature. Keep you whipping around here, guessing. Remember, we talked about patterns. We talked about things being constant. So the rest of our time here, I want to talk about gravity for a while, and then about energy. Pretty basic stuff. So here's the law of gravitation, as they call it. Whatever this stuff is, there's that same formula that we already saw with the M&Ms in it. And my little drawing, kind of homemade on the right-hand side, that's the sun on the right. and there's the Earth. There's an arrow going both ways. They pull on each other. Gravity, this invisible Elmer's glue. And I even have a little person there on the Earth, and he's being pulled by the Earth, and the Earth is pulling back on him. And there's the moon. Everything pulls on each other, and it just keeps the whole system operating. Anyway, that's gravity. We can write the formula for it, even still without really understanding how it works. Who did this stuff in the first place? Who came up with that formula? Starts with an N. You know some of these founders. It's got to be our friend Isaac Newton. So there he is. He worked with a number of things. Looks like he also worked with light. I had to have one slide with some animation in it. Remember light? On day one, God said, "Let there be light," and there it was. And it's so neat. You know, God could have just made white and gray and black. Didn't stop there. He gave us the whole spectrum, all those colors that Frank talked about as well, showing that God is an artist, and I think he did that for our enjoyment as well. Anyway, Newton did that, the light going through a prism to figure out how it all works. And then he also figured out the gravity and how the moon goes round and round the Earth. And he did this, and then he wrote up this book. And he was a sharp guy, very great intellect, also a godly man, by the way. And when Newton made these discoveries, his friend said, "Well, Isaac, I guess you've done it this time. You're explaining everything. We don't have any need for God anymore." That's what his friend said. And Newton shot right back and said, "That's not at all what I did. I'm simply exploring the secrets of how God put it together." In other words, he was a man of God. And in the next edition of his book, he wrote something like this: "The universe could only proceed from an intelligent and powerful being." Now, I'm not sure exactly what the theological position of Isaac Newton was. I've read different things, but he certainly had a high respect for his creator and was given great insight into all this. Isaac Newton, a man of God, just like most of the women pioneers from back then were likewise. I've got to say a little bit more about the moon since I brought it up. Just kind of keep colored pictures here to keep us awake here in the afternoon. There's the moon, our nearest neighbor, kind of a triple picture. This is actually an eclipse going on when the moon moves through the Earth's shadow. You've seen this before. It happens when there's a full moon, usually once or twice a year you can see this, and it lasts for several hours lately. The moon doesn't disappear, but the moon kind of gets this brownish red color. This just shows how exact and constant everything is. They can predict far ahead of time when and where this will be, and it follows the law, the celestial rules that have been put in place. I was just noticing that our next moon eclipse is February 10, 2017. Anybody got a birthday on February 10? An eclipse to go along with it? Kind of a special day. So that's one kind of eclipse. Then there's another kind, as you recall, again, following the rules that have been established when the sun gets covered. So here's kind of a tropical picture of the sun with a bite out of it. This is the moon that's gotten in front. This is a partial eclipse. Remember seeing one of these? You can't look directly at the sun, you'll weld your eyeball, but there's ways to look at it by projection. And so you can see the sun, which is partially blocked. Now, if any of the sun can get through, it still stays bright. Once in a while, the sun gets completely covered by the moon, a perfect fit. And then in the middle of the day, it gets dark and the stars come out. I've never seen one of those. It's very rare. But I wanted to tell you, hang on, because next year we have a special total solar eclipse which is going to swing right across the country. On that yellow line there that starts up just below us, it's down in Oregon, and it goes right across the U.S. and leaves down there in the southeast. Along that line, there's going to be a total eclipse. First time this has happened in 99 years. Where it's covered the whole country. So you'll be hearing more about this. It's next August 21. So the time is coming. That band where it's yellow, by the way, is about 200 miles wide, and so people will kind of be camping out along that line, and at noon on that day, it'll get dark for just about 2 or 3 minutes. When this happens, by the way, it gets cooler outside, and it gets dark, and the birds get very confused. because they settle down and nest. They think, well, that was a short day, and then 3 minutes later the sun pops out again. It'll be fun to watch that. So some of us are really looking forward to that next August. Just something to watch for. You have to travel a bit south, it looks like, from here to see it. Even though it's quite rare, when this does happen, they happen in pairs. So 7 years after this one, there'll be another one, which is going to come. I think the next one does come through Washington. We're living at a good time. We got some eclipses coming, kind of neat, kind of special. Seeing how the whole thing is arranged, how it all works, showing God's glory. There, an eclipse. By the way, along that yellow line, all the motels are already all booked. They've raised their prices. They know this thing is coming. Economics. I wanted to show you this picture. This is out of my own notes. I teach physical science back at Indiana at Grace College, and I give my students a question like this. There's the Earth, and there's the moon. Now, suppose that gravity was going to turn off tomorrow. You know, it's going to be down for repairs, no gravity. But you don't want the moon to escape. You know, the moon goes round and round, kind of caught by the Earth's gravity. If gravity was going to go away, could you replace gravity with a steel cable? I mean, you can't do this. The whole thing would get wound up and twisted anyway. But how big a cable would you need to replace the gravity pull between the Earth and the moon? What would be the diameter of that stainless steel strand cable? See my homemade picture there? So I've given you another little puzzle here, a question. To do that, if somehow you could, the thickness of that cable to keep the moon from escaping would have to be 600 what? What kind of units for the diameter? Is it going to be millimeters? Is it going to be inches? Is it going to be feet? Cubits? Well, how many units do we have here? What do you think? Can you turn to your neighbor and make a guess? Then we'll reveal the answer. How big is the cable? How big is gravity on the scale of the Earth and Moon? I keep saying turn to your neighbor. I don't know if you get any help when you do that. But we got to keep moving along here to stay on schedule. So here's the answer. It's 600 miles. Look at how strong gravity is. I mean, that cable is going to stretch clear across the state here. There wouldn't be that much steel available if you could build such a thing. And again, with the moon moving, it would get tangled up. It's just all a thought question, but it's kind of fun to do that in class. We'll get some questions at the end, okay? Appreciate it. And by the way, if you want to know actually how big that force is, if you do the numbers, it's 10 to the 22 tons of attractive force. You know what? That's a lot of zeros there. I keep coming up with that 10 to the 22. We got that this morning for the sand grains and the stars. I can't get away from it, it seems like. So there it is again. But anyway, that's kind of the answer. Hey, we're still looking at gravity here. Let me do something else with it. We've seen this equation many times. We're getting it memorized now. So again, there's the picture of the moon and the Earth, or at least two objects, and the big G and the M&M, and divided by the distance between them squared. It's an interesting equation. You see how the bottom is d squared? It's called the inverse square law. It's really the same way that light spreads out. If the car is further down the road, the headlight is not quite as bright. And that's the way gravity works. But there's a question here. Why does gravity have to follow that law? Why is it exactly d squared? I mean, that's kind of neat how that works out. And people have thought about this, so I got a little reference there, and I have this article. It's been a while here. This is in Science News magazine, and they were talking about this equation. It has always seemed a little too neat that the gravity equation has exactly a 2 in it. Why isn't that d to the 1.99 power? Or d to the 2.003 power? Why is it exactly 2? Now, it is geometric. I know the way things spread out, but why does gravity have to follow that? It just does. So in this article, they had measured that exponent, that d, as good as they could, and that's the little print at the bottom, out to 5 decimal places. It's exactly 2. This just kind of shows, you know, maybe you don't like formulas, but it could be worse. That's a nice number to work with, and it is exactly 2. That's the way gravity works. Thank you, Lord, for some simplicity when it comes to all this kind of stuff. It just, by chance, by evolution, whatever, why should it be exactly 2? But it is something to think about. Hey, let me say just a little bit more about gravity before we leave this. There's a lot of current work going on it, even though it's been looked at since Newton. Here's our current thought on how gravity operates. Suppose you had a trampoline. Maybe you have one. And let's say you take a bowling ball and you set it in the middle of the trampoline. You know how it would kind of pull down and sit there? And then if you would take that and maybe take a tennis ball and toss it onto the trampoline, can you see how the tennis ball would kind of move around and then it would probably fall in and hit the bowling ball? Well, the current thought of gravity is that it's like that trampoline. In the middle of this picture, that big green thing could be the sun, which is actually depressing space and making a dip, a low spot. And the earth is the tennis ball. And it's rolling round and round on the edge of this dip, and so it can't get away. In fact, all these objects are making dips, they're making curves in space, and that kind of keeps things trapped. So we, instead of talking about particles shooting back and forth or a cable or something, it's as if these objects are actually putting dents in space, and again, the sun making a low spot, and then all the planets kind of go around it. And you're saying, what? I don't understand, and I don't understand it either. I can see a trampoline, which is flat, 2 dimensions, but how can you do this in 3D? How can you have a low spot? All I'm saying is there seems to be some truth to this. Gravity is not simple. Maybe that formula is, but how this thing operates is something else. And by the way, just 1 year ago, for the first time, they were able to measure gravity waves, where you can have these ripples where space itself spreads out like water waves. And if this wave would pass through this room right now, you know, the person you're sitting next to, all of a sudden you'd be closer together, and then you'd be pulled apart again. Space actually like a spring or a rubber band. Maybe it's happening. Yeah, there. Now, we would notice it because we're embedded in space anyway, but it may be going on all the time. That space has a flexibility, and these things are happening. Anyway, they first detected this a year ago, and then just 2 months ago, they found another one of these gravity waves. They have 2 detectors, one in Louisiana and one right here in Washington at the Hanford site, and they both triggered at the same time. These waves are so big as they rippled across space and through the earth. Anyway, I'm just showing you just a tidbit of what we're thinking about gravity and how it operates. Well, we're describing it, but still how this all operates, it's certainly all in God's hand. Gravity, that's too much for a Saturday afternoon. Let me move on to the other part I was going to mention here, which involves energy. Hey, let's get the bottom line here. What are the 2 most basic laws in all of nature? Whether you're into botany, plants, or geology, biology, whatever. What are the 2 most basic laws? That might be worth thinking about, because it's what it all comes down to. So there's our challenge, and you've heard of these before, so it's really nothing new. They both involve energy. Here's the first one. Energy is conserved or constant. There's a certain amount. You can work with it. You can change forms, but you can't create it. You can't destroy it. There's a constant amount of energy in this cosmos. It makes the whole place dependable. A gallon of gas has an exact amount of energy. And it can change forms lots of ways. If you play your instrument, you'll make a sound. So maybe the violin string is vibrating. That would be energy of motion. And then the air molecules will vibrate. And then it'll get to your ear, and your eardrum will vibrate. And then your inner ear. And finally, in your brain, your electrons will vibrate. It can keep moving around like that, but from start to finish, it's energy going from one place to the other. By the way, there's all different kinds of energy. My goodness, I started a list, and then I just got tired of it. You've heard of some of these. And you could do a course on each one of these words here. Potential energy, kinetic energy. And there's also different units that are used, and that's over on the right-hand side. Some of those might be new to you. An erg of energy, a joule of energy. There's more units for energy than anything else, it seems like. So anyway, it's very complex and goes on, but that's energy. And again, this conservation, this constant energy. Let me pick out just one from this list here. On the left-hand side, second column, the bottom one, matter. matter is energy. In fact, you've seen this formula before. It looks like this. Energy E equals matter times c squared, and c is the speed of light. This is Albert Einstein's equation. There's theory, there's thinking behind it, but it does work. And this is just a kind of a basic form of energy. At great risk, let me try a calculation with you here. I won't figure out the sands and the seashore, but let me try this. And the writing's a little small, but I guess we can see it. Suppose you could take 1 penny, okay, 1 cent. I guess they're made out of zinc these days. But whatever it is, take that penny, and it weighs about 2.5 grams, and suppose we could take that penny and annihilate it and convert it completely into raw energy. I mean, mass and energy are the same according to that equals mc squared. So, okay, there's the formula. For the little m, I'm going to put in the mass of that penny. It's going to be in the metric system. And then c, that is the speed of light, which we also know. And I'll put that in the metric system. So here's the numbers. Oh, I do need to switch it over to kilos there because it was in grams. And wow, the speed of light, 3 times 10 to the 8th. And then you got to square it. This is why nuclear energy is so dramatic, why you get so much energy. So this is the energy equivalent of 1 thin cent, 1 penny, if you could convert it just completely into energy. And the way you convert that, there's different ways to look at it. There it is in the metric system in joules. 1 penny is also equal to 54,000 tons of TNT, or 37,000 barrels of oil in a penny. You say, how do I do that? I won't have to pay the bill anymore. All I can tell you, folks, it's a good thing that it's not easy to do this, or the bad guys would have blown up this world by now. This is nuclear energy, and it's not easy, and it takes a lot of care. But anyway, this is the energy, and it doesn't have to be a penny. It can just be in 2.5 grams of anything, a pencil or whatever. This incredible energy that God has put in all matter. It's just amazing to think about. Anyway, this is all conservation of energy, and on it goes. And let's see, I think I had a survey here. Yes, remember we have 2 laws here as we're finishing up. This is law number 1 in thermodynamics. I believe that constant energy was established at the end of the creation week. There, I'll put in the last verse of Genesis 1. God's finished putting energy into this universe from his infinite supply, and it's been coasting ever since. This law, by the way, was established by Benjamin Thompson. He was dead by that date there, but they gave him credit for it. He came up with the expression for the first law, and it's such a basic law of nature. Now, there may be some exceptions to the first law, but we can't do that. Miracles would be an exception. I think a miracle is sort of temporarily setting aside a basic law. So there I have one, John 2, the first verses. This is when water was turned to wine. Wine has more energy than water. So somehow a miracle was done there. That was converted and more energy was put in. But the one who established these laws can lay them aside or add to them anytime he wants. We can't break these laws, but certainly the Lord can modify them. Okay, we got one more law to go, and I know what some of you folks are thinking. You're wrong, DeYoung. Energy is not conserved. It doesn't work because I lost my energy. I had some earlier today, and it's gone now. What do you mean energy's constant or conserved? Man, I need a nap here on Saturday afternoon. Well, I'm glad you're thinking that way, because this all brings us to the second law of thermodynamics, which says energy kind of leaks away from us and becomes unavailable. And that's why we get tired and worn out. Everything wears out, even that old car there, the second law. It just says energy may be constant, but think about ourselves here. We're warm, so we're giving off heat to the air. It goes out in the environment, and you don't get it back again. It just goes into the atmosphere. This law is not as friendly. This one says it gets harder to work, that things break down, wear out, fall apart, and they do. Hey, let me show you another kind of problem I give to my class. Here's a drawing of a power plant. Okay, I don't know if they're burning coal or oil or whatever. Now, when they do that, they're trying to make electricity so we can have the lights on. A power plant typically takes about 1/3 of their fuel and turns it into useful electricity. And about 2/3 of it goes up the smokestack they dump it into a river, they just get it into the air and don't use it. So I ask my class students, I say, what's wrong with this picture? Are they doing that on purpose so they can charge more for energy? Are they being inefficient? By the way, the same thing happens with your car. If you buy 12 gallons of gas, 12 gallons, about 4 gallons will put you down the road, but about 8 gallons is wasted out the exhaust pipe, your car gets hot, and off it goes. It's about, that would even be good to make it 30% efficient. Is that whole thing a conspiracy to use more energy? Actually, this is the second law. You can't get around this thing. It just says that whenever you transfer energy from fuel to anything else, you have great losses and you don't get it back. There's no conspiracy. It's competitive. They're trying to produce all they can as far as energy, but that's the best that they can do. We just live under the pressure of this second law. And by the way, I think this is also theological. Remember law number 1 was creation? Well, law number 2, I put a question mark there on the left-hand side, but in some way, I think this is connected with the curse, with the fall, when things started to go down, when Adam and Eve sinned and death entered this earth, and decay and loss and even death. Somehow there's a connection there to the second law. These two both basic laws, they're both theological in nature. Anyway, the guy who worked on the second law, his name was Ludwig Boltzmann from Austria, one of those names from yesteryear. There are exceptions to the second law, but again, only miracles. There's one you might want to look up sometime, Nehemiah 9:21. I'll just leave that for you. Look that over sometime and see how that's an exception to the second law. This guy Boltzmann, by the way, was kind of interesting. Doesn't he look like a science guy? There he is. And he came up with this second law, and it's kind of unfriendly. Things wear out, it gets harder to work, and he got depressed from this and took his own life. I thought, this is interesting. That's what the second law talks about, wearing out and dying, and he followed it out and committed suicide. And when he did this, he wrote in his will that he would like to have a formula chiseled on his gravestone. And it's a formulation of the second law. And I have it over there on the right-hand side there. It's mathematical. And I was thinking, isn't that curious to have a science formula on your tombstone? Wouldn't you rather have a Bible verse? It'd be interesting to talk to that guy if he was still around and see what he was thinking. Anyway, that's his story. Hey, I got down to my last couple of slides here, and I'll be out of here. I just wanted to end with a mystery that they have when it comes to all these laws of nature. Now, here's a galaxy. Ours is called the Milky Way. There's another one called Andromeda. There's even one called Snickers. They have all these names for galaxies. And a problem has come up as astronomers look at these things. It's got 100 billion stars in it. It's turning. It's like a big whirlpool. But it's going so fast that it seems like that galaxy should disintegrate. It's like a high-speed merry-go-round. I mean, it's big and it takes a while to turn, but it is moving fast. But it doesn't. These galaxies stay together. They're stable. And so scientists can't figure out why these things don't disintegrate. And what they've decided is there must be a lot of invisible matter in the middle of this thing holding it together. There's got to be more mass than the eye can see. They call it hidden matter, dark matter, missing matter. They've been looking for it for decades and they can't find it. I'm not even sure it's there, but they say there's more that you can't see than that you can. They say 90% of the universe is missing. Isn't that kind of embarrassing? Anyway, I'm thinking of this whole problem here, these galaxies while they're still there. And just to finish up here, a verse comes to mind. Now, this is over in the book of Colossians, where it says that it's by Christ that all things consist or hold together. That would tell me that at some point, the physical world, gravity, galaxies, interfaces with the spirit world, with the Lord, with Christ. That missing matter, maybe there is no such thing. Maybe God himself is holding these galaxies together. It takes more than gravity, and he is involved. Now, folks, what would happen if for one instant the Creator would turn his back on this creation? Just turn away. He's not going to uphold the laws because they take his sustenance. The laws are not going to run by themselves. What do you think would happen if suddenly we were on our own? The atom collapses. The solar system disintegrates. all the hydrogen disappears, the galaxy flings into pieces, it would go crazy. You would have chaos instantly. This verse here is a good assurance that he's holding it together. And I got to say, he's more patient than I am with this world the way it's gone. But it's a wonderful thing how it all works, and it's a loving God that we have. So anyway, the laws of nature goes on and on. We took a quick look at it. Thanks a lot, folks.